So here we're going to talk about Lewis structures and formal charge. Lewis structures and formal charge and resonance, actually, and some examples at the very end. So formal charge, this is going to be used to determine the most plausible Lewis structure. Sometimes we're going to have multiple that could exist. So all the atom's non-bonding electrons are associated with the atoms. Half of the atom's bonding electrons are associated with the atom as well. And this is how we can determine formal charge. So formal charge is the number of valence electrons of that individual atom in its ground state. So how many it brought to the table, minus the associated electrons. And again, all of the atom's non-bonding electrons, we're going to say, are associated with the atom, and only half of the bonding electrons. And that makes sense because these are supposedly covalent bonds. So we're saying that they're shared. So only one of them is associated with the atom, even though when we're counting an octet, both of them are counted in a bonding pair. But for the point of formal charge, that's not true. And we'll actually be able to use these formal charges to determine the best Lewis dot structure. For molecules, formal charge must the sum of them must equal 0. If you have an ion, the formal charges need to add up to the overall charge of the ion. This again makes some sense. Charges are essentially electron counting. This is another form of electron counting, so it abides by very similar rules. So here we have an example of ozone, O3, and we're going to take a look at all of the, this is one Lewis structure for ozone. We have a double bond between two of the oxygens and a single bond between another set of those oxygens. So taking a look at the leftmost oxygen, we have 4 unshared electrons, which are the lone pairs, and we have 4 shared electrons, so we divide that by 2 to get 6 electrons total. So that's 6 electrons associated with the leftmost oxygen. So what we can do is we can take the 6 valence electrons that oxygen should have. So the 6 electrons that oxygen should have for valence minus the 6 that are associated with the atom, giving you a formal charge of 0. So it means that this oxygen has a formal charge of 0. We take a look at the central oxygen. It has 2 unshared, meaning from the lone pair. And then there's 6 shared, right? There's 3 bonds total. Divide that by 2. It means you have 5 electrons associated with that oxygen. So it comes with 6 valence electrons minus 5 gets you +1. So that central oxygen atom has a +1 formal charge. The rightmost oxygen starts with 6 unshared electrons. There's 1 bond associated with it, so 2 shared divided by 2 gives you 7 electrons. 6 minus 7 gives you -1. Ozone is O3. It adds up to, it is a neutrally charged complex, so the sum of those formal charges needs to equal 0, and it indeed does. 0 plus 1 minus 1 does equal 0. So this is an example of formal charges in Lewis dot structures. So let's try one of these. Let's determine the Lewis dot structure. Determine the formal charges on each of the nitrate on the nitrate ion. We're going to need to get the Lewis dot structure first and foremost if we're going to do this. Okay, so let's try draw nitrate. So we have nitrogen and oxygen, oxygen, oxygen. And we'll take a look at the, this whole thing is -1 charge. So I'm going to put that in parentheses and indicate that we're adding 1 electron to it. So nitrogen has 5 valence electrons. There are 3 oxygens. Each of those have 6 valence electrons. And it's a -1 charge, so we're going to add 1 extra electron to that. So we should get 24 valence electrons. We've already used 6, so we have 18 left over. And this will be just enough to fill the octet of all of our outermost atoms first and foremost. So this, now we've used all 18 electrons. So we're good to go. But now we need to fill the nitrogen. Nitrogen's octet, turns out it only has 6 valence electrons right now. So we're going to need to convert one of these lone pairs into a bonding pair. We could do it from this oxygen, or we could have done it from any of the other oxygens, right? So this is where this is one of the problems. And this is what brings us to the idea of resonance. Each one of those could have been completed. So that will be bringing us to the next idea of resonance structures. But for now, I'll end up showing that one of those resonance structures at the very least. Okay, that's what this one looks like. So let's go and figure out the formal charges of each of these. So I'm going to call this oxygen 1, this oxygen 2, and oxygen 3. Okay, so we have O1, O2, and O3, and the nitrogen. So we start with valence electrons. We have 6, 6, 6, and 5. You can split these into 2 categories. I sometimes do. You could do minus 1/2 the bonding electrons, and then minus the non-bonding electrons. And this should all get you to formal charge. Okay, so we can go and just fill in this table. So oxygen 1 has 6 valence electrons, minus 1/2 the bonding electrons. This you'll sometimes see as minus number of bonds, which is also true. So 1/2 the bonding electrons is 2. Non-bonding, there are 4 total, right? So oxygen 1 has a formal charge of 0. So oxygen 2, 1/2 the bonding electrons. There's only 1 bond there total, so that ends up being 1 and 6. This is also 1 and 6. And lastly, nitrogen, it has 4 sets of bonds to it, and no lone pairs. Okay, so this means that we have 2 oxygens that have a -1 formal charge, and this nitrogen has a +1 formal charge. If you add up all of those, that does in fact equal -1, which is the charge of the anion, which does make some sense. Okay, so like I said, it was arbitrary that we picked oxygen 1 to be the oxygen that has a double bond. And like I said, this will lead us to another idea of resonance structures. But in the structure that we drew here, it means oxygen 2 and oxygen 3 have a formal charge of -1, and nitrogen is a +1 charge. This does mean that they would be partially negatively charged and partially positively charged, for example, and it does give us some indication of the actual chemical structure that's occurring in that situation. But this is how you would go about determining formal charges, and we'll also use these as metrics to determining a better or worse resonance structure in the future. Or I should say better or worse Lewis dot structure, and they'll sometimes be in the form of resonance structures. Okay, so in determining which one's better, if you have multiple different arrangements of atoms, we can select the best one using formal charges by these guidelines. If you can have something that's neutrally charged and all the formal charges are 0, that's going to be the best situation, as opposed to ones that have non-zero formal charges. Secondly, if you do have to have formal charges, we'd prefer them to be small formal charges. Zeros and plus or minus 1 are going to be definitely preferred in comparison to +2 or -2 or +3 and -3 and so on. And lastly, the best Lewis structures are going to have formal charges consistent with electronegativities. So if you have to have a -1 formal charge, that would preferentially be on the most electronegative atom. If you had to have a +1 formal charge, preferentially that would be on the least electronegative atom, sometimes called the most electropositive atom. So here's another example where we can take a look at the connectivity and see which one is preferred for formaldehyde. So we can use formal charges here. to determine which skeletal arrangement is the best choice for CH2O. So number of valence electrons total. The hydrogens we are always going to ignore. You're not terribly concerned about the hydrogens. Those should have a formal charge of 0 always. So we're going to take a look at the number of valence electrons. We have 2 from hydrogens. From the hydrogens, we have 4 from our carbon, and we have 6 from our oxygen. So we should have 12 total. Each one of these have already used 3 bonds, so that should be -6. So we should have 6 more electrons to complete these Lewis dot structures. So here, if we have 6 more on this, we would do, we've added 6. So I've completed my octet of my oxygen first and foremost, and then started adding them to carbon, which is less electronegative. And I think you can see here, carbon needs 1 more bond. So I'm going to convert one of those lone pairs on the oxygen to a double bond. So first we'll erase these lone pairs here, because now I've used all of them, all of my electrons, and do a double bond here. Okay, so that would be the structure for that. We'll do the same thing with this. We'll fill the octet of the outermost atom first. Okay, here we did that. I think you can see again, we're going to need to convert one of those lone pairs into a bonding pair. So we'll create a double bond there and erase one of those lone pairs. All right, so here are 2 Lewis dot structures that we are trying to compare. Let's see how this works. So valence electrons, we're really only looking at carbons and oxygens here. So there's 4 for carbon, 6 for oxygen, 4 for carbon, 6 for oxygen. That's that, right? So half the number of bonding electrons. So here we have 3 bonds and 2 electrons. For oxygen here we have 2 electrons and 3 bonds. Over here for this carbon, we have 4 bonds and no lone pairs. Here oxygen we have 2 bonds and 4 electrons for lone pairs. So here you can see we get formal charges of zeros. Well, over here we have 4 -3 -2 gives you a -1 on the carbon, and then we get a +1 on the oxygen. So both are valid Lewis dot structures. Sorry, +1. Both are valid Lewis dot structures, and their sum of their formal charges do add up to 0, but this is going to be the greatly preferred Lewis dot structure because its formal charges are 0 as opposed to -1 and +1 on the carbon and oxygen. So the magnitudes here are what dictate that this structure on the right hand side should actually be the structure for formaldehyde, and it is. Okay, so lastly, resonance structures. I know I've been alluding to it a little bit here already. When we have one of 2 or more Lewis structures for a single molecule that can't be represented accurately by only one Lewis structure, then we need resonance structures. The problem with Lewis structures is we have to show exactly where the electrons are, localized in one individual area. That is sometimes not the case, which is what's so challenging about this. So that's why we sometimes have to do that. So this first example, it was ozone. It was arbitrary which oxygen we decided to form the double bond with. So we will often show this double-sided arrow is what we mean by resonance structures, and we're only moving the location of electrons. That's the only thing that we're doing. So here, if oxygen 1 is on the left-hand side, you can see we're switching where that double bond is. So these would be 2 resonance structures. Likewise with carbonate, same thing, which is kind of the issue that I alluded to with nitrate. Here we're forming a double bond with one of these oxygens. We could form that double bond with oxygen 1, oxygen 2, or oxygen 3. So these are three separate valid Lewis dot structures that are resonant structures to each other. They all will also, none of them will be better than the other. Sometimes one will be better than the other based on formal charges. In this case, they're all equivalent. So you could almost say that they're hybrids. If you could jam all three of those together all at once, that would be the real molecule, the real carbonate molecule. That first structure seems to indicate that there's a double bond between one of the carbons and one of the oxygens, where there's a single bond with the other two. But that's not true. If we were to look at carbonate in the real world, all of the carbon-oxygen bonds are identical in length. And that means that it's really a hybrid between these three different resonance structures. So since we have to localize where those electrons are, each one of these resonance structures has some issues associated with it. It doesn't perfectly represent carbonate as it exists, but we can consider them, all three of them together, as being a pretty good proxy for what carbonate is. Here we have a practice problem. Draw all the resonance structures for sulfur trioxide, SO3. Should be noted that this is assuming that sulfur obeys the octet rule. We haven't talked about whether it does or doesn't. We are assuming everything does. Sulfur can break the octet, which we will talk about later. But for now, we're assuming sulfur obeys the octet. So let's just draw some of these resonance structures for SO3. Sulfur and oxygen, they both have 6 valence electrons. There are 4 total atoms, so 24 valence electrons is what we should have. So just quickly fill the octet of the outermost atoms. This does get us to 24 valence electrons total. You can see sulfur has only 6 valence electrons currently, so we're going to need to take valence electrons from one of the oxygens. You can see we can do it from this oxygen, or this oxygen. So we're going to need to draw all 3 of those. All 3 of those will be 3 different resonance structures associated with sulfur trioxide. Again, this is assuming that that sulfur obeys the octet. Okay, so here this is one of them where we have this sort of setup, and again we'll be able to do the same thing for the other 2 oxygens. To form those 3 different resonance structures. There's no charge on this, so I don't need to put this whole thing in parentheses and indicate the charge. So this would be the second resonance structure. Again, convention is a double-sided arrow in order to say that these are resonance structures of each other. So I can do that again to get my final resonance structure like so. All right, so here are the 3 different resonance structures associated with SO3. And we'll find in the future, using this example, how there's an even better resonance structure than this once we learn some more about exceptions to the octet rule.